Hello everyone and welcome back to Ananthu Explainer. Take a moment to consider the technology that surrounds us. Your smartphone, the LED light, the vast infrastructure. All of it at its very core relies on an incredible, often unseen force, solid state electronic devices. These aren't just components, they are the result of deeply understanding and precisely engineering materials at the atomic level. Today, we embark on a conceptual journey to unravel these fundamental building blocks of modern electronics. We'll explore the profound physics behind their operation, providing a concise yet in-depth explanation of how these devices function and ultimately how they power our world. This is our project to demystify solid-state electronics conceptually. At the heart of all solid-state devices lies in the semiconductor. Unlike conductors that readily allow current or insulators that strongly resist it, semiconductors possess a unique characteristic. Their conductivity can be precisely controlled and modified. Our primary material is silicon, an element with 4 valence electrons, forming strong, stable covalent bonds in a crystalline lattice. In its pure intrinsic state, it's poor conductor at room temperature. The truly ingenuity comes from doping, intentionally introducing minute amount of impurities. When we add a donor impurity like phosphorus with 5 valence electrons, 4 bonded with silicon leaving 1 extra electron loosely bound. This creates an N-type semiconductor where electrons are the majority carriers and the Fermi level shift closer to the conduction band. Conversely, adding an acceptor impurity like boron with 3 valence electrons results in a missing bond, effectively creating a hole. This forms a p-type semiconductor where holes are the majority carriers and the Fermi level shift closer to the valence band. This precise engineering of carrier concentration is a foundational principle for all subsequent devices. When an N-type semiconductor meets a p-type semiconductor, a profound phenomenon occurs. The p-n junction is formed. Initially, majority carriers diffuse across the junction, recombining and leaving behind the ionized impurity atoms. This creates a region devoid of mobile carriers known as the depletion region, which possesses an inherent built-in electric field. This field acts as a barrier. When we apply an external voltage in forward bias, positive to P side, negative to N side, this applied field opposes and effectively reduces the built-in potential. This lowers the energy barrier for majority carriers, leading to substantial current flow primarily due to minority carrier injection. Conversely, in reverse bias, positive to N side, negative to P side, the applied voltage adds to the built-in potential. This widens the depletion region significantly, creating a larger energy barrier. Consequently, only a little reverse saturation current, primarily due to the thermally generated minority carriers, flows until a critical breakdown voltage is reached. This fundamental unidirectional current flow makes the diode indispensable for applications like rectification, converting AC to DC, voltage regulation. From the diode, we advance to the transistor, the revolutionary device that enables both amplification and electronic switching, the bedrock of all digital computing and complex analog circuits. We focus on the bipolar junction transistor, typically an NPN structure, a thin, lightly doped p-type base sandwiched between a heavily doped n-type emitter and moderately doped n-type collector. It essentially features 2 interacting p-n junctions. The key to its operation lies in controlling the current flow across the base emitter and base collector junctions. In the active region, a small forward bias on the base emitter junction causes electrons from the emitter to inject into the base. Since the base is very thin and lightly doped, Most of these injected electrons diffuse across the base and are swept into the collector by the reverse biased base collector junction. This results in a fascinating phenomenon. A tiny input current into the base dramatically controls a much larger current flowing from collector to emitter. This is the essence of amplification. Operating the transistor between its cutoff region, that is no base current, no collector current, and saturation region, that is sufficient base current, transistor is fully on, and allowing it to function as a high-speed electronic switch. This ability to control large currents with small signals is what makes microprocessors, memory, and every digital device possible. Solid-state physics also enables the elegant conversion between electrical energy and light, giving us optoelectronic devices like light-emitting diode, that is LEDs, and photodiodes. An LED is specifically designed PN junction, where forward-biased electrons from N side and holes from the P side are injected into the active region. Here they recombine in specific direct bandgap semiconductor materials. This recombination energy is released directly as a photo, which we perceive as light. The color of the emitter light is determined by the specific bandgap energy of the semiconductor material itself. Conversely, a photodiode is also a PN junction, but it operates in reverse, converting light into an electrical signal. When photons with sufficient energy strikes the photodiode's depletion region, they absorb the photon's energy, creating a new electron-hole pairs. The strong electric field within the depletion region then sweeps these generated carrier apart, producing a measurable photocurrent. And this is the fundamental principle behind light detection, optical communication, and even solar energy conversion. These devices are crucial for displays, fiber optics, sensors, and even renewable energy. Now let's bring these fundamental concepts together in a tangible project idea: a smart home sensor. Imagine a device that intelligently detects ambient light levels and provide an indication, perhaps for smart lighting control and environmental monitoring. At its core, this sensor would utilize a photodiode or a similar light-sensitive component to precisely measure incoming light intensity. This analog light signal is then converted into an electrical signal. This electrical signal feeds into a control unit, which in modern designs is typically a microcontroller. This tiny chip is an incredibly complex integrated circuit housing millions, even billions of intricately interconnected transistors that process the sensor data and execute logic. Based on programmed thresholds, the control unit can then activate an output. For instance, it could send a signal to a power transistor, operating it as a high-speed switch to turn on an LED indicator or even a large smart light fixture. And importantly, the system's power management would rely on PN junction diodes for rectification and for protection against incorrect polarity or voltage surge. This conceptual project elegantly illustrates how the individual solid-state principles we've discussed are synergistically combined to create intelligent, automated systems that enhance our daily lives.
Individual electrons in precisely doped semiconductor material to creating unidirectional current flow with diodes and enabling complex logic and amplification with transistors and bridging the electrical and optical worlds with LEDs and photodiodes. We truly glimpsed the profound impact of solid-state devices. These devices working in intricate harmony are far more than just components. They are the fundamental language of modern technology. They empower us to design and build everything from the smallest, most sophisticated sensors to the most powerful supercomputers, driving innovation across every industry. I hope this conceptual journey has provided you with a clear, in-depth understanding of the amazing solid-state devices. They are, without a doubt, the unsung heroes powering our modern world and shaping the future. If you found this explanation insightful and professional,
Please hit that like button, share it with anyone curious about the fundamental physics of electronics. Don't forget to subscribe to Ananthu Explainer for more deep dives into how things work. Thank you for watching.